Are you there, Lucas?
Yes, I'm here. Yeah,
Okay.
just getting ready to.
So we have, okay, thank you. We have Lucas Nellen from the ICN UNAM with the plenary cosmic rays in the era of multi-messenger astronomy. So go ahead, Lucas. Thank you.
Okay, so I assume you can see my slides correctly.
Yes, we can. Thank you.
Okay. Okay, good. So I've looked a bit at what to do with this topic, and after listening to the talks here, I've tried to tune it a bit to what I hope will also be of interest to your community in what I'm talking about, but in part it will be generic about cosmic rays and about multi-messenger astronomy. So the first part, if we talk about multi-messenger astronomy, I'm here interested in doing it for the extreme universe, for the most energetic objects, not for lower energy objects. So we have, when we talk about multi-messengers, we're always thinking about the different modes we have, or different carriers we have that bring us information from some source that we're studying. And obviously the most used ones are neutral stable, and of those photons where we do astronomy, obviously since prehistory in the visible range, and as instruments got better, we added radio, infrared, ultraviolet, X-rays, gamma rays, which is part of what I'm interested in. Recently, neutrinos have become part of the multi-messenger scenario, gravitational waves. Then there are neutral unstable, which I'm not going to talk about, but in some cosmic ray scenarios, neutrons could be produced and could live long enough to become interesting messengers. Then there are charged cosmic rays, which are complicated. I'm going to mention that a little bit in a moment. And then there's related dark matter, which we could detect indirectly, or which could mix with what produces cosmic rays. So we don't really observe it directly, but it plays into the field when we're doing cosmic ray physics. And those that are highlighted here, gammas, neutrinos, neutrons, cosmic rays, and the indirect dark matter, those are the messengers or the particles we detect in our instruments, or we can say something about instruments. And therefore, in the sense of multi-messenger astronomy, work together with instruments that detect objects in other channels, gravitational waves, or the different photon detections. And here, so this is a picture of how this would look like from the point of view of cosmic rays. Here, this is drawn for Auger. This is the Auger site. This is the telescope array site in the north. So it's ultra high energy cosmic ray centric, this drawing. What is important here to see is all the neutral particles come in nice straight lines, see neutrinos, photons. So you can easily detect sources. With cosmic rays, we have the problem that the universe is full of magnetic fields, maybe a bit more complicated than these little dipoles that are drawn here. But it means that at lower energies here, the energy range 15 to 18 electron volts as an example for proton. Particles do complicated random walks, diffusive, and the direction at which we see them on the Earth is not correlated to where they come from. So especially they do not point back to sources. If we go to the highest energies of the order of 10 to the 20 electron volt, about 100 electron volts, then the curvature of the particles, if they're protons, can be down to 1 to 3 degrees. And given the fact that there are very few possible candidate sources, you have error boxes that are small enough that you can start thinking about doing even charged particle astronomy with them. So this is what we're aiming at eventually, or one of the aims that we would eventually like to do at high energy cosmic rays. But what I want to talk about here is really what we're doing with two instruments where we're working with, where we have international collaborations with Mexican collaborators too. So one is the HAWC Observatory, which is actually located in Mexico, and the other one is the Auger Observatory in Argentina. So I guess this is a Latin American centric presentation here by selecting what I'm thinking. So the HAWC Observatory is in Mexico near the Pico de Orizaba, which is the highest mountain in Mexico, I think the third most prominent mountain in the Americas, towards the coast of Veracruz and more or less on the line Mexico City, Veracruz. The Pico de Orizaba is 5,636 meters. It has a smaller twin, which is only 4,560 meters, which hosts the Large Millimeter Telescope, which most of you might have heard of, or directly or indirectly, because it's one of the members of the Event Horizon Telescope. So, and there in the valley between the two, in a saddle, which makes it sufficiently flat, we have HAWC. It's big enough to be seen even on Google Maps here at 4,100 meters. If you zoom in with HAWC, you see 300 water strength detector stations. So what looks like these mushrooms, we have electronics building for data taking in the center and the service building on the side. And each of these detectors is about 4.5 meters high, 7.3 meters diameter, about 220 tons of water. Here you have me as a reference. Well, it doesn't help you because I'm not standing in front of you. So another reference is these tanks are about the size of a Tyrannosaurus Rex, if that's more useful for you. What we've done to HAWC in recent times is we've added smaller tanks here. These are 2,500 liter tanks. We've instrumented each of them also with a photomultiplier around it, which increases the area here by about a factor 4 and allows us to increase sensitivity above about 10 TeV. We are currently adding this data set, the processing of this, to our data set. This hasn't been analyzed yet. They've been in operation for about a year and a bit. And the other experiment I wanted to include in what I'm talking about is the Auger collaboration. It's a bigger experiment, a bigger collaboration, 17 countries, about 460 collaborators. You see international collaboration, Australia, a number of European countries. The UK, unfortunately, has dropped out, but you still have Italy, Spain, Portugal, France, Romania, Germany, Poland, the Netherlands, all there. Then the US, Brazil, Argentina, Bolivia is an associate country that's also participating, and there's Colombia too. The Auger Observatory, you saw it on the map before, just for the start. This is actually roughly on the line between Buenos Aires and Santiago de Chile, just before you hit the Andes from the Argentinian side. It covers about 3,000 square kilometers. The reference for us here is about twice the size of Mexico City. So this is a pretty big observatory. It has about 60 kilometers diameter. It has a bit over 1,600 surface detector stations, each of these dots here on this hexagonal grid, with a denser infill area to get to lower energies, plus buried muon detectors to add more composition sensitivity, and four fluorescence detectors. Each regular station has 6 telescopes. Here there are 3 the heat telescopes that are angled up to allow us again to observe to a higher angle to lower energy, together with the corresponding ground part. And this means we have full coverage of the surface area with fluorescence, and at higher energies we see stereo events. We've actually seen up to quadruple events if a very high energy event falls in the central region. There's also here experimental radio detection area. So we're using it not only for active detection, also for developing of next generation experiments. And if you want to characterize Auger in a nutshell, you could call it a an air calorimeter of 3,000 square kilometers geometrical aperture and about 2.5 times 10 to the 10 tons of mass. This is an interesting figure because this is in the same ballpark as like cubic kilometer of water. So for certain types of neutral particles, this explains why Auger does similar well than to IceCube. So the individual stations, there's the water Cherenkov stations, so they're smaller tanks than the ones we had in HAWC. In the Pampa Amarilla, you can see a bit from the coloring, it's not the luscious green, but it's a bit more dry area. You still have a few gauchos coming around, but the tank itself is about 12 tons of water. We have electronics on top, batteries, the 3 photodetectors inside. The tanks have to be autonomous, so they have solar panels with batteries, and then communications and GPS to communicate to the central station. The fluorescence are these buildings with the 6 telescopes, communication, the LiDAR, which I'm not going to talk more about, but it's for atmospheric monitoring, which is important when you use the atmosphere as part of your detector. Each telescope is a Schmidt telescope. It has the UV filter, which is at the same time the window. It has a aperture that is larger than what you would normally have in a Schmidt telescope design, with a corrector lens to allow us to collect more light and reduce the signal to noise ratio, with a spherical mirror and the curved camera, which is all typical for Schmidt optics, with 440 photomultiplier tubes. So this was a quick tour over the observatory. Now I'm going to go slow down a little bit to give you details of how we do things. So what we're detecting are the air showers. So it's the primary particle, which can be a high energy photon, but it can be a cosmic ray nucleon. In principle, it could also be an electron or positron, but they don't really exist much at high energies because they in the galactic magnetic field, due to synchrotron losses, they just drop down in energy very, very rapidly. So that population they're not part of the population that we detect. But what happens is, so in the atmosphere, we get a whole cascade of secondary particles, of pions, which feed into photons, electron positrons. So we have an electromagnetic part of the cascade. We have the hadronic core of the cascade that goes more down the central part. If the same gets started with a photon, that would be the case for gamma in HAWC, you would only get an electromagnetic cascade with very few muons and neutrinos inside. But what still remains the same, this cascade basically moves at the speed of light, but it opens up a little bit. So you have something which is strongly forward beams, but it comes down like a pancake or a tortilla that comes down more or less at the speed of light, slightly curved. And at the same time, you get ionization of the atmosphere that can produce fluorescence light that can be detected at clear moonless nights from the side with fluorescence. So you can see the longitudinal development at night, and what you can always detect is in those different detector stations, the shower front. You can see this part will be hit before that part. So what you get is really a very nice geometrical reconstruction. Basically, velocity and time gives you the distance, and you can actually see this here in this fit by eye. You can see the perpendicular plane just by drawing the timing. This is done actually for the Milagro detector. You could do the same for HAWC, but I don't have that plot. So this part just shows you getting directions is actually fairly easy if you have a neutral particle. The problem with charged particles is not detecting the direction at Earth. It's really the fact that they don't point back to their sources. So now, how do we measure energy? This is a bit more difficult. what we really do, and this depends a bit on the exact detector, but we basically estimate the signal from the signal in the ground detector at the reference distance. That is we estimate the energy. So this distance, the 1000 here is a kilometer. That is always in relation to the detector spacing. This 1000 is a good number for the detector spacing of 1.5 kilometers at Auger. That by itself just gives us a number correlated to the energy. We have to calibrate this. In the case of Auger, we use the fluorescence detector to calibrate the surface detector energy scale. And this has been done by basically looking at how does the fluorescence light grow and then drop with the depth of inside the atmosphere. This is actually a very simple trick. The ionization that you get is proportional to the number of charged particles in the shower. And the number of charged particles goes with the development of the cascade. So what you're basically doing is you convert the energy of the primary particle into lots of number of secondary particles. So the energy measurement gets converted into a counting experiment. So that's really all that happens here. You count the number of secondary particles that you can produce, and then up to some missing energy because neutrinos you won't see and so on. You can basically say that the energy is proportional to the area under this curve. So you have a nice calorimetric scale, which is good. You don't need simulations to do this. You can really do this from first principles, which makes it fairly robust. Then you can, and from there you calibrate your surface detector energy. And then you can use a surface detector which works 24 hours a day to get statistics. The fluorescence detector has a duty cycle of around 10%, so only about 1 in 10 events will be accompanied by fluorescence data. You can use similar techniques to calibrate other SD observers. I don't think I'll go into much detail. I mentioned 1 or 2 later on. If you don't have a fluorescence detector, you could do the calibration with Monte Carlo simulations. That's what we do in HAWC. But you have the problem that you need to model the particle physics processes, especially for the strong interactions at high energies, and there you just get additional theoretical errors that you avoid with the direct calibration as we do it in Auger. So if you can do it, you try to avoid simulations. If you can't, well, you try to do the work with the best simulations you can get. There are a few more tricks to get the energy to get the depends on this from the zenith angle removed. I don't want to go into the details here how to do that, but with this kind of curve you compensate for the attenuation of the shower. As you go to more inclined showers, you have more atmosphere to go through, so you get fewer particles on the ground. By something else, which is, but now coming to the part which you want to is you have to do photon identification if you want to do if you want to do gamma ray physics with those experiments, and especially for HAWC, which is designed as a gamma ray observatory, that's absolutely necessary. If you don't have particle IDs, your experiment would be useless. So what you do is use the fact that, as I mentioned before, a gamma will only give you an electromagnetic shower, which is much more smooth, and most signal is sort of like in a reference circle, compared to a proton where you have a rough front and you have detectors with a large signal like here or this block, which you can see there, outside a reference region. So you can look for large energy regions, large energy deposits further away from the core, or you can just look for the largest signal outside the reference version, or you can use basically look at how cylindrical symmetric is your signal, or how well can you fit a curve that is characteristic for electromagnetic showers to this, and all of them pretty well as as tools for characterizing, for identifying the photons. And recently, we're adding machine learning techniques to that. And that has a fairly high efficiency in HAWC. In Auger, it's a bit more difficult, but you use, in that case, the fact that photons, because of the lower cross-section of electromagnetism, enter deeper into the atmosphere. So you can see, this is where you would expect the maximum of a shower development in the atmosphere for photon. This is where we observe them between proton and iron. These lines, again, because you go from lowest cross-section electromagnetic photon to medium, which is proton, and iron, because there's 56 nuclei, has even higher cross-section. You see the data goes in between those. And this allows you basically to tag photons and limit photons. You can do it only with a surface detector where you can't see the shower maximum. Again, from the geometry, if a shower is deeper in the atmosphere, then it corresponds, then the front will have a larger curvature, if you can just see here. Or you can get these rise time parameter. If a shower is deeper in the atmosphere, going along the two edges of a triangle will have a larger distance than if the triangle is more collapsed when you're high up in the atmosphere. Each of them by itself is not a good parameter, but you can see here in this principal component analysis that they allow us to separate pretty well photons from protons. You get a few protons in entering the photon region, but if you put a hard cut, you can really eliminate false identification of photons, and that gives you very good photon limits. And this is interesting here, because if you look at the comparison of data, and the best data is the Auger hybrid data here, the lowest points that we have going down, and you compare them to different scenarios. If you have high energy propagation of protons, you would expect them to interact with photons of the microwave background, which would give you delta resonances, gives you pions, gives you photons at high energies. So you can sort of like estimate a photon background at high energies that should be there if your highest energy cosmic rays are photons. You can see we're getting into that as limit. And here the other curves are Z-burst, topological defect, and different decaying dark matter models. And you can see here the photon limits of Auger exclude some of these exotic structure formation dark matter scenarios pretty strongly already. If you assume that those are also sources of cosmic rays, if they would be decaying so that the source of photons, they would also be sources of protons. So that connects Auger limits with some possible scenarios from the early universe. Another of the messengers which is interesting is neutrinos. HAWC can't say much about neutrinos, but to see how do we tag neutrinos, we use the geometry of an air shower. As I've mentioned already before, in the case of photons, you get the curvature of the front depends on where particles get produced. So if you think you have a region of most activity around the maximum of the shower, you would have the far region, which gives you the outer front, and the closer regions gives you the inner front, which gives you like two spherical shells which touch in the center but separate. So closer to the core, the two shells touch. The signals come pretty much in a very short time window. As you move further away, the signals are more spread out. Now, if you look at the same, but for a shower which is much further away, the separation is not as big, so you get similar separation in both regions. And if you do it for neutrino showers, neutrinos you basically detect in very inclined air showers using the atmosphere as a shielding. That's how you can do neutrino detection, even though you're not in a deep underground detector. You have enough atmosphere above you that that not many particles, that only particles of with very low cross section can come very inclined. You get the scenario where, well, instead of tilting the it's easier in this graph to tilt the ground from the vertical, which would be to a very inclined shower. So you would have a shower which in the early part looks like a young shower, a shower that is close, where the detector is close to the active region. But in the late part, it looks like an old shower. So you would have a very different signature in detectors that are early in your event and detectors that are late in your event. Or to repeat this, hadronic showers, if it's a hadronic shower, it's inclined, it has to develop far away from the atmosphere, from the detector, because it has to develop up in the atmosphere. So it's an old shower and it's mainly muons. If it's a neutrino, it's a young shower, and neutrinos can even come up through the ground if the tau neutrino converted not too far away from the surface of the Earth, and then the tau decays above the detector. Here, another interesting number: the atmosphere is about 1,000 grams per square centimeter. That's how much atmosphere we have above us. That corresponds to about 10 kilometers distance at 90 degrees. That explains why the shower really develops from an young shower to an old shower along the detector that has an extent like 60 kilometers, like Auger has. And you see this again, what I mentioned before. The early detectors have a slow broad signals. The late detectors have a fast narrow signal. And this is how we're tagging neutrinos. And we're getting good neutrino limits from that, comparable to the limits that are IceCube or Anita beats us at the highest energies. IceCube beats Auger at the lowest energies, but Auger and IceCube get down to similar lowest levels. This is again compared to here to different theoretical models. Some of the cosmogenic models are starting to get excluded by the Auger limits on neutrinos. So far, we have neutrino. This is something we're still waiting for. But we're pretty confident that our neutrino detection works. So, and what we're actually doing, this is where we're really getting into more interesting, I think, for your community, especially multi-messenger astronomy, is doing follow-ups. We've done since the first gravitational wave triggers were released, follow-up with Auger. This is the region where Auger is most sensitive. The very first event completely fell outside our sensitivity. The second one had a pretty good overlap with Auger. This funny shape is because we basically seeing in the horizontal. So instead of seeing a part of the sky as a spherical kappa, as you would normally do with a telescope when you look up, what you're actually seeing is like an annulus of the sky, where the neutrinos would come from near the horizon. That's why our acceptance has a very funny shape when projected onto the sky. So this was sort of like something we did when the first triggers got publicly released, and we decided we can actually do something with gravitational waves. We decided that Auger decided to sign an MOU with LIGO, and this was fortunate. So when the famous neutron star merger, the 1708-17 event came out, we had also an MOU with us. As you all know, this got detected as a gravitational wave event, and with a signal shortly after in the Fermi gamma ray burst monitor, and integral, which confirmed that this was indeed a short gamma ray burst, which is exactly what you expect from theory of gamma ray bursts to be the signature of a neutron star merger. Other instruments, the LAT instrument of Fermi was already turned off. Hess and HAWC were also looking at the wrong part of the to see the signal. They saw it later and just established limits. So, but this was a perfect moment for neutrino telescopes to work in. And actually, this event was in the most sensitive region of Auger. Here you see the location of the event on the sky. This darker band narrow is the Auger maximum optimal sensitivity in the Earth skimming neutrino channel. The wider band is additional sensitivity. If you compare it to the ice cube, which has a fairly flat acceptance on, and Antares, which could just barely see it, Auger was in the perfect, or put it the other way around, for someone who's just waiting for an event, this event just came at the right moment to be at the perfect maximum sensitivity for Auger. This was not a very powerful event, so nobody would have expected strong neutrino signals from there, and we didn't see any neutrino signals, so all we could do at this moment was establish limits, but both with HAWC and Auger were part of the big multi-messenger observation, and we have this extra neutrino limits paper of LIGO with Antares Ice Cube and Auger, and the Auger limits here in the short time window are the strongest. If you look at the 14-day time, the limits get Auger moves up because the source moves out of the optimal region. But you can see that some of the models are already ruled out, but only the very optimistic models. But this is important since then all the gamma ray and neutrino experiments are listening to gamma ray, to gravitational wave triggers. So far, we have only limits established, but one day, hopefully some interesting neutron star may happen at the right position. We'll see neutrons. Another part which is interesting is sources of cosmic rays, which is anisotropy. As I said at the beginning, protons get sort of like really diffused about, like stirring a drop of ink in a glass. You don't know where the drop was originally. Quite interesting that we do see at high energies above 8 × 10⁻18 electron volts a dipole. This was actually sufficiently surprising, and it was a 5 sigma detection that it was mentioned as a top 10 breakthrough in 2017. So what you see is you very clearly see the signal in the first harmonic in right ascension. You can even see a hint of a modulation if you add the second harmonic. What it does is at the end, if you have the dipole and you put it onto the sky, the dipole points into this direction. And these two errors, this is a galaxy catalog, the mass density in there. So the dipole already by eye goes roughly to where you have lots of galaxies. And if you take into account magnetic fields, depending on the energy, and with the typical magnetic field models we have for magnetic fields, this displacement is more or less comparable. So there is a hint that at high energies, the cosmic rays are correlated somehow to galaxies and are not correlated to sources inside our galaxy. You can really see that this dipole at lower energies is small and it becomes visible at high energies. In recent papers, we can really, what used to be just one point in 17 by now is, you can see, we have enough data to start resolving this into several points. We see the increase of the dipole. If you look at it in different ways and compared, and you bin the energy in, you bin the events in energy, you can see at low energies, which is here the smaller dots, the anisotropy points a bit into the direction of the galaxy.
We have
yes?
5 minutes left. 5 minutes.
Okay,
left.
yes. So the anisotropy points towards the galactic center, which is where more mass is. So it's not surprising we are off center. So if galactic cosmic rays, we expect a slight over it from the center, but as the energy goes up, it moves away. So it's a sign again that the dipole is not galactic. We've looked at different models for this, and there's no clear model, but there are several models that could explain anisotropy. And then in the last 5 minutes, I want to quickly go over another way, which is more now HAWC-centric, the possibility of limits on Lorentz invariance violations from high energy gamma rays in this case. Auger also works on this, but we don't have a result yet. The basic way is if you get a modified dispersion relation, you get a modified speed of light. So you can do time delay studies, and you can look at those, and you get the. And this is how most gamma ray experiments have been doing this in the past. You can do simple analysis techniques with a minimum and maximum photon time, but the problem is that this really works with 2 photons, and it has to make strong assumptions about the emission at the source. You can make it more sophisticated with more analysis, which are not ideal for HAWC because they generally require a larger number of photons. They were really developed for experiments like Fermi or MAGIC or HESS for the Cherenkov telescopes. But instead of going into the details here, I want to mention the technique which allowed us to really get a good result, which is looking at limits from photon splitting and decay. You know that normally Lorentz or relativistic kinematics forbids photon decay because of the zero mass. But the moment you have violation of Lorentz symmetry, you get an effective mass term for photons. So the photons can decay, and the distance scale at which they decay is very odd compared to astronomical distances. So you get a very sharp cutoff above a given threshold. The thresholds are here compared for gamma to E plus E minus. You can also have a photon going to 3 photons. Yet the limit gets a bit different, and it becomes distance dependent. So if you look at this, what we've done is we've taken several of our highest energy sources where we have events detected from between 120 to 244 tera-electron volt photons. This year, the J05 34 plus 220, that's actually the Crab nebula, which is here listed in this fit as Crab. So we fitted spectra, and we compared this to a fit with the assumption that we have a hard cutoff, and come to the conclusion that this is not compatible. This establishes here the different limits, which in this display is more easy to see. They're actually here in all cases the most competitive limits. These limits here, the GRBs, these are limits, for example, using this delta T methods from gamma ray bursts. And just as a reference, about 10 to 28, this is the Planck scale. So our limits really exclude Lorentz violation up or above the Planck scale. There's many things that I couldn't cover today. For example, the part of multi-messenger is the M1 observatory, which tries to do automatic correlations of lower energy events between multiple experiments. More details about how cosmic rays and magnetic field studies work together, limits and studies together with other ground-based and satellite instruments, for example, studies done with correlation HAWC and IceCube or HAWC and Fermi, or how we do dark matter limits in high energy gammas. And in the future, what we're working on is being the Auger to get better primary particle ID. In this context of represented here, it's particularly important to get a photon enhanced data set with higher rigidity, better pointing towards sources. And then the new instruments, LASSO, which got recently online. It's a HAWC-like instrument, but has a square kilometer area. The Cherenkov telescope array is the next generation of the follow-up experiment to MAGIC HAWC Veritas as the definitive ultra-high energy gamma ray observatory, and then the Southern Wide Field Gamma Ray Observatory, which is a Hawk-like instrument in the southern hemisphere. Even LASSO, we've recently discussed that we probably also want to go to a square kilometer with LASSO. So that's what I had to present to you today. Thank you very much.
Thank you, Lucas. Very nice talk. So we have time for one question or one comment. There is something in the chat. I don't think so.
Can I make a question?
Yeah, go ahead. Very quickly.
Very quickly. Okay, thank you. Thank you, Lucas, for your interesting talk. I have just one little inquiry. How can you perform the calibration of your GRB?
Which part of the calibration? You mean the neutron star merger?
Right. Mm-hmm.
For us, we just use as Auger, we just assume, we just look at our normal neutrino calibration procedure, which has quite a bit of Monte Carlo to get involved to get all these subtle details look and to establish our neutrino sensitivity to then decide what's the flux limit we can set. And for the rest, it's just the normal the regular gamma ray burst community that has models that predict different levels of neutrino emission, and we just compare them to our observations. So we don't have to do a special calibration for that event. It's just our regular neutrino detection procedure.
Oh, okay, good. Thank you.
Thank you. Thank you, Lucas. Nice talk. So now it's time